Alright, so here we're going to be talking about surface area and volume of these three-dimensional figures. So these are all the formulas that you see on your formula sheet. You also have this little set of abbreviations that you can always use if you're unclear on what something is in an equation. Some of these are really straightforward. Some of them you need to actually think about finding missing sides or missing parts before you actually plug into the equation. So we're going to go over just a series of questions dealing with just cylinders, spheres, and rectangular prisms for now, and then the other three shapes are each going to have their own videos just because there's some intricacies to those that I want to go over in detail. So we're just going to start off by dealing with a practical problem dealing with this basketball or a sphere. I think a sphere is honestly the easiest shape just because there's only one measurement or one variable that comes along with a sphere, and it's just the radius of that sphere. So we're told that the circumference of the basketball is 29.5 inches. How much air will fill the ball? So this is looking for the volume of that basketball. How much air will it take to fill the space inside the ball? So we know the circumference. We can use either pi times diameter, or what I'm going to use 2 pi r, just because that actually already has the radius in it, and that's what I'm searching for the volume. So I know the answer to that. I know the circumference is 29.5 inches. I'm going to use that to work backwards to solve for that radius. So I'm going to divide by 2 pi on both sides. So 29.5 divided by 2 pi. And I'm always just going to round pi to 3.14. That gives me 4.6974. I'm going to round that to just 4.7. So I'm going to take that radius and then plug it back in to that volume equation to actually solve for the air that can fit inside of that. You have to make sure that you're following order of operations still. So we have to do our exponent first and then the multiplication. So 4.7 times itself 3 times, and then times 3.14 for pi times 4, and then divided by 3 tells me that the volume of that basketball is 434.67. I'm just going to round that to 7 again. And that's inches cubed. Anytime we're talking about volume, whatever units we have, it's going to be cubic units because it's actually literally talking about the number of small cubes that will fit inside that shape. When we're dealing with surface area, it would be inches squared because it's actually talking about literally the number of squares that it takes to cover that shape. So here we're going to be talking about the regular patterns that develop when we change an attribute or all the attributes of a shape. So when we change just one attribute, really what I'm saying is that we take something like the length and we multiply it by 3. So if that happens in a rectangular prism, if I took this length, multiplied it by 3, let's change that L into 3L, you could see that that has the exact same effect on the overall product there. The volume will also triple. If I do that same thing and I consider the surface area, that's not as regular of a pattern. If I triple the length, it's going to affect this term, it's going to affect this term, but it actually doesn't affect that third term. So it's a very regular pattern when I multiply the length times any scale factor. That same scale factor gets applied to the volume, whereas that's not really the case with surface area. And actually, you're going to notice that's kind of true for most of these shapes, just because there's different variables that come into play. If you just change one, it might not affect all parts of that shape. Same thing with the cylinder. If I affect the radius, it affects this just factored in there one time, but it actually has an exponent of 2 here, so the effect on that first part is different from the effect on that second part. So the surface area, just in general, when we change one attribute, is affected a little bit irregularly, whereas or at least it's more complicated. It's regular, but it's more complicated. The volume is usually very straightforward. If I take that radius and I multiply that times 3, this is a little bit different from before. If I take that radius and I replace it with 3r, so instead of that r, I'm going to put 3r in there, and I'm going to put it in parentheses, which is really important. I'm taking that whole quantity of the radius and tripling it. That's going to actually get squared also. So if I think about my exponent rules from last year, that gets distributed into both of these. And really, the overall effect on that, I don't know why I put that in parentheses, didn't really need to. The overall effect is really whatever the scale factor is squared, because the radius is getting squared. So the effect on the radius when I go to the volume is squared, whatever the scale factor is on just that radius. It's a squared scale factor when I think about the volume. If I affect the height by that same scale factor, let's say I change that into h, that has the exact same effect as with a rectangular prism. If I triple the height of the cylinder, it triples the volume. And then, actually that effect is the same for a surface area of a sphere. You can see that the radius is still squared, but then you notice for volume, that radius is cubed. So let's say I did that exact same thing. I'm taking that radius and cubing it instead. So I can see my exponent rules would also cube that scale factor. So whatever scale factor gets applied to just the radius actually gets cubed for the volume of a sphere. So here would be a factor of 27. So that is when we just change one attribute. It has that compounding effect for a sphere because that's the only attribute that we have for a sphere. It has less of an effect for volume of a rectangular prism because we have 3 different dimensions. It could have an exponential effect on a cylinder if we affect the radius, because that's the squared part of that, but it could also just have a linear relationship if we affect the height. Similar figures have all of the attributes affected by the scale factor. So in a rectangular prism, it would be multiplying the length times 3, the width times 3, and the height by 3. So all of those get affected. These have very regular patterns. The ratio of the surface area, so let's say we wrote our scale factor as a fraction, which would mean, in this case, it would be 3 to 1. The effect is squared for surface area, and the effect is cubed for volume. So whatever the scale factor is, that effect is compounded by whatever measurement we're looking for. The scale factor, this is talking about really the edges of the shape. This would be doubling the length, width, and height. This is talking about the actual surface that covers the shape. That has a squared effect because the actual units are square units. Volume has a cubed effect because we're, again, just talking about little cubes that actually fit inside the shapes. And that is a very regular pattern that we see with similar figures. So here we have a picture jar that shows the company's original jar design. Fortunately, those dimensions are not available. The company must decide between 2 other options for a new can. To save money, they want to choose the option that holds less, so we have a smaller volume. That's what we're thinking about when we're talking about how much something holds, talking about the volume, and we're really just looking for which of these 2 options will hold less. So option A has the same height as the original design, but its diameter is twice as long. Option B has the same diameter, but it's 3 times as tall. So you could go ahead and actually change these dimensions and then find the new volume of each of these designs, but we have a much faster way of doing this. If I double the diameter, I'm doubling the radius. So if I think about the volume of a shape like that, that's pi r squared times h. If I change the radius by a factor of 2, I change that into 2r instead of just r. That really has a multiplying effect of 4 on the volume. That 2 is getting squared. That effect is squared because I'm affecting the radius. So really, that would lead me to 4 times the original volume there. If I triple the height, it only has a factor of 3 that it's increasing the overall volume by. That's multiplying by 3. That's multiplying by 4. So option B is definitely the lower volume between those 2 options, and you don't actually need to find the exact number. We just know that the comparison to the original one leads to that one being the smaller one. Here we have 2 spheres that have a radii of 5 and 9. So the radius of that guy is 5, the radius of this one is 9. What is the ratio of their volumes? So I'm going to think about these ratios as the big to small. You could also frame it the other way if you want to think about small over big, but I want to think about what I can do to this radius to get up to that new radius. And really, my ratio is directly here. This times 9 over 5, that would be the scale factor that I would use to increase it to that size for just the radius. Now I want to think about what effect that has on the volume. So the volume of a sphere is 4/3 pi r cubed. So I'm thinking about if I take that radius and I multiply it by that scale factor, 9/5, what effect does that actually have on this overall volume? And you can see that that 9/5 is also going to be cubed. So if I'm just thinking about my exponent rules, that gets distributed into all parts of that fraction. I guess you could also write this as a decimal. That might make it a little bit easier. In general, we're going to see ratios as fractions, though. So that cubed gets applied to everything inside of there. So we cube 9, that would be 729. We cube 5, that's 125. So that's the change in between this original equation, and when I apply that scale factor to just the radius, that's the scale factor that gets applied to the overall volume. So my scale factor or ratio between my volumes is 729 over 125. That effect was cubed because we're dealing with the volume of that shape rather than just a length. Sorry, that's not what I meant to highlight there. A length within that shape. All right, so here we're going to be talking about the lateral area of these 3D figures. Lateral faces are the faces that are on the side of the shape, not including the bases. So in a triangular prism, which is what we're seeing there, it has a triangle base on top and on the bottom, surrounded by these lateral faces on the front, and there's one in the back that we can't really show there. So the bases are the top and the bottom, sometimes just the bottom, like we see in a cone. The lateral face or lateral area is the side that's going, really wrapping around the base. So pyramid and a cone have one base each. The area that goes around the outside up to the peak of that pyramid or cone, that's the lateral surface. And you can see that there's actually equations on your formula sheet for just those parts. But to be honest, we really don't need those. They are all just parts of the full equation. So you can see on a triangular prism, you see HP in the lateral area. You also see that pop up in the total surface area. Plus, we add in the base on the top and the bottom. We add in those two bases. Same thing is true on all of these. Really, we see the circle on the bottom, pi r squared, plus the lateral surface. That's the total surface area. So the lateral surface is just the distance, or sorry, just the area that covers the outside of the shape, not including the bases. And this visual, that animation, gives a pretty clear picture of where this part comes from in the surface area of a cylinder. This distance, that's now moving around, that distance is 2 pi r, because it's really just the circumference of the circle, times the height. That's the area of that rectangle. I kind of missed my opportunity, but that's what that's showing. The circumference times the height. Those are just the dimensions of that rectangle. So the height of this Pringles can is 5.5 inches. The diameter is 3 inches. How much material is used just for the label of the can? So we're not talking about the top and the bottom at all. We're just talking about the lateral area of that cylinder, just this second part. We're not including the two circles, which is really all that's showing. 2 pi r squared is just talking about the two circles on top and bottom. So we're really just finding this part of it. So we're going to use lateral area is 2 times pi times the radius, which is 1.5, times the height of the can. So that tells us that that total area would be 51.81, and we're talking about inches, so it's area, so inches squared. One more little thing to talk about, really just the comparison between the volumes of a pyramid and a prism, and a cone and a cylinder. It's clearer in these equations, but it's the exact same relationship. You can see that is the volume of a cylinder, pi r squared times h, pi r squared times h. This is just 1/3 of that, and that's what this visual is really showing, that a cone would fill in 1/3 of a cylinder. That relationship is the same between pyramids and prisms that have the same base. This is a rectangular based prism, so we find the volume just using length times width times height. This looks like a rectangular based, or maybe a square based pyramid. So we would find the area of the base using length times width, then times height, then times 1/3. You can see that that is exactly 1/3 of this volume. This is left as a capital B on your formula sheet because this base is going to change. Sometimes it's going to be a triangle, it could be a hexagon, it could really be anything. And the same thing goes for a prism. So if they have the same base with the same dimensions and the same height, then the volume of a pyramid and prism has that same exact relationship as a cone and a cylinder.